Good morning, everybody. Today we're going to be looking at full symmetrical parabolas. Now, this is one of the hardest topics people have to grasp this year, so please pay close attention. We are going to be looking at a diagram, just the way we started with half parabolas. So in the diagram, I am going to be using colors to separate the two planes. So just to remind you, I'm going to be using blue for the horizontal motion. I'll be using green for the vertical, and I'll be using red for resultants or anything else, okay? All right, so we're going to look at a classic example, a football kicked from the ground and it lands on the ground. For example, at kickoff, the place kicker kicks the ball and it goes downfield and they just let it hit the ground and roll. Of course, we're not looking at the roll part, just until it hits the ground. Once it hits the ground, it's no longer a projectile anyway. All right, so here's the ground. And here's our little football. Okay, and we're going to kick it down the field, so it's going to make a beautiful parabola that looks something like this. And then it hits the ground somewhere downrange. Okay? All right, so we're going to be looking at several points along the path, just the way we did with the half parabola. So we'll start with this one, and maybe we'll look at this point, and maybe the point right at the very tippy top. Another one here, and then right here where it reaches the ground. Okay? Now, let's start with the fact that when the ball leaves the kicker's foot, it has an initial velocity. That initial velocity has two components. The initial velocity is at some angle theta, and if we break that initial velocity into two components, one component is horizontal. I'm going to call it the initial horizontal velocity, v sub I h. The other component is going to be the initial vertical velocity. All right, the sum of these two make the initial velocity at that angle of trajectory. Now, if you know the two components, obviously you can put them tip to tail and you can use the Pythagorean theorem to find the magnitude of the resultant initial velocity and inverse tangent of the tangent ratio to get the angle. But what if they give you the initial velocity and trajectory angle and that's it? What if that's what they give you? What if they give you the hypotenuse and the angle? This is where we learned about that skill last week, vector resolution. If you are given these two pieces here, the hypotenuse and the angle, then we know the horizontal piece is found by saying the hypotenuse times the cosine of the angle, because it's the adjacent leg. And the vertical velocity at the beginning is found by saying hypotenuse times the sine of the angle, since it's opposite the angle. Okay? So don't forget about that skill. It's important. Okay? Now, I would like to focus for a little bit on just the horizontal motion of the projectile. That's it, just the horizontal motion. So let's take a look. Once the ball leaves the kicker's foot and is a projectile, the only force acting on the football will be gravity, but gravity is in the vertical plane. So, because of independence of perpendicular vectors, it has nothing to do with the horizontal velocity. Since there is no other force to affect the horizontal velocity, that velocity stays constant for the entire trip. Okay? So if we're careful and we try to draw this the same size, when we get to the end, the final horizontal velocity is going to be the exact same value as the initial. Okay? That has to be true if it stays constant. That also means that there is no horizontal acceleration. Oh, I meant to put an H there, not an X. Well, you can use X, but I'm going to use an H to be consistent. All right, there is no horizontal acceleration, and nobody's ever going to tell you that, just like they didn't with the half parabolas. It's assumed that you will understand this to be true because it is a projectile, okay? Now, the object will have an initial horizontal velocity, which stays constant because there's no acceleration in that plane, and it will travel downrange, a distance we'll call dH. And remember, another word for that is range. Okay? And it will do this in the hang time we'll call T sub H, the horizontal time or hang time. Okay? So, D, V, well there it is, V, A, T. There's our four variables, D, V, A, T. Now, right at the moment, this sounds an awful lot like the half parabolas. And yes, it is for any projectile. I don't care what shape the parabola is. The horizontal motion is always going to be constant velocity with no acceleration. Okay? So, in fact, right now, while we're talking about the horizontal motion, let's do this. We're going to describe the horizontal motion two ways. We're going to describe it in English, and we're going to describe it mathematically. In English, we would say the ball, or whatever the object is, has an initial horizontal velocity which, wonderful, remains constant.
If you have found a set of 2 house keys on a lanyard, would you please
hang on.
notify the front desk as soon as you can? Extension 71938.
Okay.
Thank you.
All right, so the ball has an initial horizontal velocity which remains constant. Mathematically, we would describe it using the general equation. We'd say dH equals V sub IH times T plus 1/2 AH T squared. But because the horizontal acceleration is 0, this term completely drops out, and we're left with the part that describes constant velocity. So that's what we'll use. Okay? All right. Now, if you'll shift down to the bottom while we're talking about the horizontal motion, let's look at the graphs of the motion. Okay? On the first axis, we're going to make this the position time graph. So we have the position in the x direction, positive x, and position in the negative x. This is horizontal. Remember? Horizontal. So horizontally, we have negative x and positive x. All right? And we're going to look at what happens to the position through the hang time. All right? Well, back here, we'd say the ball starts at 0, at time 0. But by the time it gets here and the motion stops, it has traveled dH in time TH. So where is DH? DH is going to be somewhere up here, right? And at time TH. So at TH, we're at DH. Now, how do we get from here to here? We do it at constant velocity. M equals V sub IH, which is constant. Constant slope, constant velocity, right? Okay. Now let's look at the velocity time graph. We have velocities in the positive direction. We have velocities in the negative direction. And here's the time T sub H. Now, when the ball leaves the foot, it has some horizontal initial velocity, V sub IH. And what happens to that? Well, nothing. It stays constant for the entire time, all the way out to the hang time. Okay? It stays constant. So here the slope is the horizontal acceleration, and it's 0. How do we graph that on an acceleration time graph? Easy. Okay, if it's 0, well, let's put the hang time out here first. If it's 0, it's going to be right along here. Okay, so constant velocity, that means consistent change in position over time, and constant velocity, and constant velocity. No acceleration. Got it? Okay, that's pretty much it for the horizontal motion. That's easy because it's like the half parabolas. But what about the vertical motion? Let's take a look at that. We're going to come back up here to our picture, and I'm going to use green now for vertical, so let's look. We already know that when the ball leaves the kicker's foot, it has an upward initial vertical velocity. Now, one thing we have to understand is we know that velocity is going to change. In fact, we already know that somewhere up here it comes to a stop and then it comes back down. But I want you to notice there's 2 directions now. There's not just one direction down like we had with the half parabolas. Now we're going up and then coming down. Because of that, we have 2 different directions in the same plane. They cannot both be positive directions, so we need to decide right now what we're going to do about that. All right, so I'm going to come over here and I'm going to indicate, and this is typical, I wouldn't say it's standard convention, but most people typically take moving upward to be the positive direction and downward to be the negative direction. So now all vectors in the vertical plane that point up will be positive. All vectors that point down will be negative. Okay? Now let's look. As the ball moves upward, this vertical velocity decreases until right at the tippy top, the vertical velocity at the top is 0. There is none. It stops briefly. Now, does that mean the ball itself is stopped completely? No, because look, you still have a horizontal velocity, but no vertical velocity. So yes, the ball is moving, but not vertically. All right. Now, in fact, if we draw the resultants of these, you can see that the resultant gets smaller and smaller and changes direction, okay? Until all you have is horizontal at the top, okay? So there's your resultant at the top too. It's just the horizontal piece. Now, once it has stopped, then what happens? Well, now it's going to start coming back down. So the vertical velocity will begin to increase. Notice the direction. Now it's negative, and you're adding a negative increment to it. So the negative velocity gets bigger and bigger until when you get down here at the end, the final vertical velocity is the same magnitude as the initial, but it's in the opposite direction. Isn't that kind of cool? All right. In fact, if we connect these tail to tail, tip to tip, we can see that the final velocity overall has the same magnitude as the initial. It's just pointed at the same angle below the horizontal as opposed to above the horizontal. But the magnitudes, the numerical values, will be the same because the components are the same values. Okay? All right, now, why does the velocity change in the vertical plane? Well, because of gravity. So we know we have a vertical acceleration, the acceleration due to gravity, and on Earth, it's a value of 9.8 meters per second squared. But now hold on, where does it point? Acceleration due to gravity always points down, and down we have defined as the negative direction. So we're going to stick a negative on there. and put a star right here to show that that is an understood piece of information they're not going to tell us. Okay? Now, so we've looked at the velocities and the accelerations. Let's talk about displacement now. The ball starts on the ground, and vertically, it ends on the ground. So where have you gone? Nowhere. The total vertical displacement for the entire trip is 0. And they're never going to tell you that for a full symmetrical parabola. They're going to expect you to understand if it vertically starts and ends at the same location, that's a 0 displacement. Now, it doesn't start and end horizontally at the same location, but here goes up, comes back down, ends on the ground. You end up back where you started vertically. So 0 vertical displacement. Okay, so we have 0 vertical displacement with a velocity that changes by increments of negative 9.8, and it does this all in a time t sub v, which happens to be the same as t sub h, right? Because both motions take place concurrently, that is, in the same time frame, together. All right, one last thing I think I want to talk about for just a minute is, again, the point at the top. There's one more piece of information. I want to talk about the fact that we know that the hang time is the total time for the trip. That's the total time for the trip. But what I'd like to know is, how long does it take it to get to the top of the parabola where it stops vertically? That's going to be important because we would like to be able to determine at some point the height that the object reaches. In this case, the football reaches at the highest point. How far is it above the ground? Well, think about this. This is a symmetrical parabola. It starts on the ground. It decreases by increments of 9.8. Then you add those same increments back, and it hits the ground. These two halves of the parabola are symmetrical. So it's going to take the same amount of time to go up as it does to come back down. Therefore, the time it takes to get to the top, the time to the top is 1/2 the total time. 1/2 the hang time. Because of symmetry. Symmetry can be a wonderful thing. Okay? All right, now let's do what we did with the horizontal motion, and let's describe it in English and math. Now that we've talked about it and looked at pictures, let's actually describe it formally. All right, first in English, look right here. The ball has an initial vertical velocity. It doesn't start from rest here. That was the half parabola, but not here. The ball has an initial vertical velocity. Now, does it remain constant like it did in the horizontal plane? No. All right. It decreases or decelerates upward to a stop. Okay, then what does it do? It increases or accelerates on the way back down. So, and accelerates back down. Okay? If you wanted to stick the word uniformly in, you could. You could say it uniformly decelerates upward to a stop and uniformly accelerates back down, but most people understand for projectile motion on a planet that it is uniform. Let's do it mathematically now. With a general equation modified for verticals, we'd say d sub v equals v sub iv times t plus 1/2 avt squared, where in this case you could also replace av with g, okay, before you plug numbers in, you could just say g. But notice, in this case, this is not 0, this is not 0, and if you're looking at the total time, this is 0. But I don't want to drop it right now because sometimes you're not looking at the total time. Sometimes you want to look at the point at the top, in which case you'd have half the total time, and the vertical displacement would be the height. In fact, one thing you need to understand is whatever point in time you put in, it'll tell you how far above the ground you are. For example, if the total time for this was 2 seconds, and we wanted to see where's the ball located at 1.5 seconds, we'd put in 1.5 seconds, we'd put in our initial velocity and the acceleration, and we'd stick it in the calculator, and it would tell us how far above the ground the ball is at 1.5 seconds. You could put any time in and see where it's located vertically. It's just that a lot of times we specifically want to see where it is at the top. How high is it at the very top? And we know that's where half the total time is passed. So you stick in half the total time, you get the height, the maximum height reached. Okay, so that's what we're going to use for the vertical, all of it. Okay? All right. Now, let's take a look at the answers to these questions and see if we can answer them now that we've talked about it. It says, how much time would it take a projectile to reach the top of its path for a full symmetrical parabola? Well, we've talked about that now. We said because of symmetry, it takes half the total time. So, right here, the time to get to the top is 1/2 the total time. Okay? Now let's try the next one. When the projectile hits the ground, how does its final velocity compare to its initial velocity at the beginning? Oh, we said they have the same magnitude. Okay? So, they have the same magnitude. That's because the components have the same magnitude. If you had 4 and 6 here, you'd get 4 and -6 here, and when you use the Pythagorean theorem, you're going to get the same magnitude hypotenuse. Okay? Now, what is the net velocity of the projectile at the top? Well, let's look. Here's the horizontal piece. Here's the vertical piece. All right? So, square root of v sub I h squared plus 0 squared, well, it's just going to be v sub I h. So, the net velocity at the top is going to be just this. V sub I h. Okay? Because the other component is 0. The vertical component is 0. In fact, we could put that right there just so you'll know later, because v sub I, v sub v top equals 0. So all you have is that. What's the net acceleration at the top? Well, let's look. For the whole trip, the horizontal acceleration is 0. For the whole trip, the vertical acceleration is -9.8. So what's the net? It's -9.8, right? So the net acceleration at the top is just going to be the vertical, which is -9.8 meters per second squared, because the horizontal is 0. Okay? All right, last thing, let's take a look at the graphs for the vertical motion. All right, let's take a look. Here we go. All right, so vertically, let's start with position, and I'm going to use a Y for position because we're on the Y-axis and we're talking about up and down. So positive is up, and negative is going to be down. Now, where does the ball start? It starts on the ground. Ground is typically taken to be 0. We don't usually go below ground, do we? So for this graph, we typically aren't ever down here. All right, here's the hang time. Well, maybe I should put a V there for vertical, but it's still the hang time. And what we do is we see the ball, position-wise, travel up until we get to the height at the top of the parabola, And then it comes back. Well, I can't get my paper to sit still. Hang on. Oh, that's terrible. Oh, well, you can draw yours better than mine. So there you go. You get a parabola where the point at the top, half the total time, that's where you've reached h, the height at the top, okay? All right, now let's look at the next one. Let's look at the vertical velocity. So we have the upward directed vertical velocities, and we have the downward directed vertical velocities. Remember, positive is going to be up here, negative is down. That's what we decided. Here's 0, here's the hang time right out here. Okay, so what do we have? Well, we know that the ball started with an initial vertical velocity. And it ended up with a negative final velocity that's the same magnitude as the initial. Negative final vertical velocity out here at the hang time. And halfway through, we stopped at the top. So we started with this velocity, we decelerated uniformly to 0, changed direction. See, we're still going up. We're going up, 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 up. We're just slowing down as we go up. And then we accelerate back down. When we hit the ground, we're traveling the same speed as we were up here, just in the other direction. Okay? So we're going up, 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 but our velocity is decreasing to a stop at the top. Then we change direction. Now we're coming down, 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 but our velocity is increasing in the negative direction. You starting to get it? Okay, last one. Excuse me. Sorry. Okay, so acceleration time graphs. The vertical acceleration in the upward and down direction. We only have one acceleration. Notice the slope is negative. Sorry, allergies. We have a negative slope, so we have a negative acceleration. We even know its value. It's negative 9.8 meters per second squared for the entire hang time. Okay? You're adding the same negative increment to your velocity at all times. So there's that one. Okay, so positions, velocities, and accelerations at each point in time up to the hang time. Okay? All right, we're going to stop right there. Yes, I know there's an example here, but I'm going to have another video in your folder with tomorrow's assignment that goes through this. I figure if you see it right before you start the assignment, it will be fresher in your mind. Okay? So that's it for today's notes, and tomorrow we're going to work on the problems. Okay? All right, see you then. Bye-bye.